first slide, which is a recap of the last lecture. So maybe some more students will join by then. Okay, so let's continue then. So Imtiaz is here now. Okay, so yeah, so in the last class we looked at that was on Thursday, last Thursday. The reason for changing the midterm was because some of you have requested that you need more time because of those rains, and the second thing was I was finding a little difficult to prepare a midterm paper which would be suitable for you students, keeping it open book and open discussion, open lectures, open notes. So uh, I was thinking of giving you some case studies, but then I thought then it would be a little difficult for you people. So I said, okay, let's give. Let me just have some time for you people to study a little bit more, and then we can have it by next week. The second thing is the government is going to have its session on 7th September, and they are going to decide whether they are going to go for online or they are going to go for some physical classes as well. So if possible, we can have that at campus. I'm going to see whether we can do that as well. But for the time being, it's been delayed till the next Sunday, and we are going to have uh, a complete picture by Monday or Tuesday of what's going to happen for undergraduates, for the master student. For undergraduate students, they are having their final exam also online. So this has been decided last week, but I'm not sure if that's going to be there. If that's going to be decided for master students as well. Okay, so in the last class, what we did was control hazards, and in control hazards, we looked at why control hazards occur, right, and how to reduce their stalls. So one way to reduce the stall is to decide, or you can say do all the things required for branch earlier, in an earlier stage. For example, in a decode stage, you can do easily the you can easily calculate the branch target address, as well as the condition can be evaluated, but it would be a little difficult for the condition to be evaluated there. So one thing that can be done is to predict the condition, and if you can predict the condition accurately most of the time, then it's going to give you a lot of benefits. Because it's a prediction, you can go wrong. This means that if you go wrong, then there would be a penalty. Otherwise, you're going to save many cycles. So we looked at different prediction schemes as well in the last class. We looked at static branch prediction. We looked at dynamic branch predictions. Static is done at compile time, so you cannot change those predictions while the program is running. While in dynamic branch prediction, you can start with any prediction, but as the program grows, you can change those predictions. And then we looked at a simple branch history table kind of thing, which can be a 1-bit branch history table, or a 2-bit branch history table, or it can be an n-bit branch history table. It depends on how many bits you have in your history table. Because there are just two options, so what we do is the number of bits you have has got 2 raised to power m combinations. If there are m bits, you have got 2 raised to power m combinations. This means that for half of those combinations, you're going to go with one prediction, and for other half, you're going to go with the other prediction. Then we look at the correlating branch predictor, which is not looking at only the local history, but it also looks at the global history of other branches, because it assumes that this branch has got some correlation with the earlier branches that have executed in the code. So this assumption is not wrong, because many of the times your branches have got some linkages. So if the earlier branches have behaved in a different way, then you are talking about how is this branch going to behave. So in a correlating branch predictor, what happens is we have multiple branch history table entries for the same branch depending on how the earlier branches have behaved. And we looked at one of those correlating branch predictor like G share, which was using a hash to index into the memory. um, then there are tournament predictors where there are multiple predictors running, and then there is a selector which can select whichever is performing well, which means that because it's a prediction, the branches are also going to execute in a particular stage, and then their actual outcome is going to be known. So if the actual outcome and the prediction are accurate, are correct, if the actual outcome matches the prediction, this means that predictor is predicting good. So the selector's job is to select that particular predictor, and if there are multiple predictors and one of them is continuously giving good predictions, then the selector is always going to favor it. But if some other predictor is going to give better predictions, then the selector is going to shift to that predictor. So it shifts between predictors, and then there is no constant predictor, and then there can be different predictors. This was about tournament predictors, and tagged hybrid predictor was the reading assignment. Then this was about branch prediction, but then there can be also the other thing, which was a branch target address. So we can have some scheme for knowing the branch target address as well. And for that, we have branch target buffers. Now, the branch target buffer is the small cache, and it stores the branch address. Along with the branch address, it stores the place where that branch has jumped. So the address of that instruction where the branch has jumped, which is the branch target address. So what happens is whenever you're going to fetch an instruction without knowing or without decoding that instruction, you are going to just check through that branch target buffers. And if there is an entry for that particular address, this means that it's a branch instruction, and it's a taken branch. So you can always go to the branch target address immediately, because in the next cycle, because the entry is going to be there. So if a branch jumps to one place within a code, then it's always going to jump to that place if it's going to jump, right? So if it's a taken branch, then it's going to jump. If it's a not taken branch, then that entry has to be removed from the branch target buffer, right? So this was about control hazards, and this completes, not the completes, but this is one portion of the ILP that we have covered. Then we are going to come to another topic, which is memory hierarchy, and then we are going to come back to some of the remaining topics of instruction level parallelism. We're going to talk about multi-cycle operations. So here we have just talked about single cycle for every stage, but if the execution stage has got multiple cycles, like division operation has got many cycles to complete, and multiplication has got many cycles to complete, then how is the pipeline going to behave? We are going to come to that after we have finished the memory hierarchy topic. So our next topic is memory hierarchy design. And when we come to memory hierarchy, the main thing is that the programmers want unlimited amount of memory, and also with low latency, because they need their programs to run fast. But the problem is that the fast memory technology is very expensive, and obviously we cannot have that for the whole memory system, because not only is this expensive, the other thing is that it also consumes a lot of power. So even if you have the whole memory designed by the fastest memory you have, it's going to take a lot of power, and then the design is not going to be suitable. So the solution for this is to organize memory in a hierarchy where you are going to have both slow and fast memory. So the thing with slow memory is they are slow, but the technology that is used is quite cheap, and then this means that per bit cost reduces. So the overall design cost is it's going to be less, because you have a mix of high-end technology, which is fast and expensive, and a low-end technology, which is slow, but it's cheap, right? So a solution is to organize the memory in a hierarchy, and we have multiple memories from slow to fast. and each memory is going to contain a subset of the data. For each memory in this hierarchy is going to contain the subset of the data from the earlier level. Now my question is, so you people have studied memory hierarchy in an earlier course or undergraduate level, obviously. So my question is, why is this concept working? How is this concept working? I mean, um, the problem is that we need fast memory and we need bigger memory, right? But we don't have fast and bigger at the same time. So all those memory which are big are slow, and all those which are fast are you cannot use them for the whole memory design. So the solution is to have a mix of that. But why is this working? Because if there is a slow memory, or if I come over here, right? So if there is so our idea is to have multiple memories, right? So there are different memories here which are drawn, like for example, according to the sizes. And if this is the CPU, right? Okay, so if this is my fastest memory, so I'm going to call that as T1, and this memory has got time T2, and this memory has got time T3. So T1 is less than T2 and it's less than T3, right? So this is what we have assumed. And if you talk about the capacity, so let's talk about C1 as or space. In terms of space, let's call that S1 and S2 and S3. So S3 has got the highest space, then S2, then S1. So I'm not talking about the cost right now, but cost is again the same thing, that the first level has got the highest cost and the second is cheaper than the third one, but it's cheaper than the first one, but it's expensive than the third one, and the third one is the cheapest, right? So I'm not talking about the cost, I'm talking about the time and the space, the storage space. Now, when the program needs some data, so it has to fetch that data from memory, and this is a small memory. The one which we are calling the fastest is a small memory. So this means that it cannot contain the whole thing, right? So the whole thing would be somewhere here in the slowest memory. Okay. Now my question is, when we say that we have a mix of memories, so why is this concept working? Because if I need something and I cannot find it in the first level, then obviously I have to go to the third level, right? So if I go to the third level every time, now previously I was just, if let's imagine we don't have T1 and T2 and just T3, CPU is directly accessing T3, then this means that CPU is accessing at the time of T3 time units, right? But now if there are multiple levels in between, this means that the CPU is going to go to T1 first, to the first level first, and the second level first, and then if it finds there in the third level, then the time required to fetch that data is not T3, but it's T3 plus T2 plus T1, right? So time has increased. Instead of reducing the time has actually increased. So instead of the CPU getting that data directly from T3, if there were no T1s and T2s, that these two levels, then if the CPU is directly accessing the highest, the biggest memory, the slowest one, so it's going to access it by the time of T3. But if you are going to introduce two more stages into it, then the time to get that data would be T3 plus T2 plus T1, right? So, but we say that memory hierarchy is going to give us low latency. How is this possible? Yes, anyone. How is this possible? Because previously, if we were just directly accessing T3, that time would be T3. But now we are going to search it over here, T1. If we don't find our data, then we are going to do it over here, T2. If we don't find it over here, then we are going to go over here. So the total time would be the sum of all those times. Okay. So then you say, then you have that data in your first level, right? So if now you have your data in your first level, you can access that from time t1, right? But this level is a small level, right? It cannot hold everything. So if it cannot hold everything, then if the CPU needs a lot of uh, references from that program, then T1 cannot satisfy that. The first level cannot satisfy that particular request, and then you are continuously going to go to the third level, right? So if you continuously go to the third level, this would be the time. So why are we saying that this memory hierarchy is going to benefit us? I think it's going to give us more time. Yes, anyone?
Sir, सर इट विल बी वेरी लेटेंसी एट द फर्स्ट टाइम बट जब मेन हमारे पास जो लार्जर मेमोरी है वहाँ से एक ब्लॉक आएगा T2 में, तो उसका साइज थोड़ा लार्जर है, तो कुछ ब्लॉक वहाँ पर स्टोर हो जाएगा. सिमिलरली द रिमेनिंग ब्लॉक विल बी शिफ्टेड टू द T1 एंड फिर ये रेफरेंस के थ्रू डायरेक्टली मेमोरी फैचिंग करेंगे. वेरी स्टार्टिंग में टाइम कंज्यूमिंग बहुत ज़्यादा होगी, लेकिन उसके बाद फिर हमारे पास ये प्रॉब्लम सॉल्व हो सकता है.
um, the the problem still remains, because what you are saying is that, okay, so we are not going to bring a block, so we can have some whole amount of data transferred, and then we have some. But my question is, but this is a small memory; it cannot contain the whole program, right? So if it cannot contain the whole program, then these references that you have brought, you can access them by the time T1, which is smaller time. But if the references run out, then you are going to still fetch it from the last level, right? So if you're going to start executing your program, and then you're always accessing the third level, this means that the time that you're going to take would be more than previously, where you had only the third level.
Sir, hello.
Yeah, I can hear you.
Uh, that depends what the data we will store. Maybe the most repeatedly need will put it in cache 1 or in T1.
Okay, so the thing is that the first level is small level, right? So it cannot hold the whole program.
Not
So
whole program. The
yeah,
most that we need most time data that we need most time we will store in T1 and the
okay,
other in another different level.
okay. So you have come to that point, but still you need a little just to you need a little bit to improve it. Okay, Yasir was saying something as well. I'm going to take
Sir,
some. Yeah.
can we attach suppose a virtual memory, just like RAM, in order to speed up the
Uh,
process?
no, virtual memory is a different concept here. So I'm going to come to that as well. But virtual memory is there. So you can see it's something like these
In terms of RAM,
addresses.
you can say.
These addresses which the CPU are going to generate are going to be virtual address. That's the concept of virtual memory. So this memory, whatever you are saying, is actually is actually a virtual memory. So the CPU generates a virtual address, but that address cannot be found over here or here. Then it has to get it from the third level. So if it get that thing from third level, then the time would be T3 plus T2 plus T1, right? So the time has actually increased, right? But um, if there is a T1 over here, what's the use of this T1? Why are we getting benefits?
Sir, sir,
Yeah, Imtiaz.
yes, sir, Imtiaz here, sir.
Yeah,
Sir, the most important chunk of our memory we have to store in our T1.
yeah. Then
Yes, yes, sir. Then the other important, the last priority uh, chunk of the memory we can store in the T3 stage. So this is actually the hierarchy system. The
Um,
files which we need.
okay, but why does it work? I mean, how does it work? Most important. So how can I give you an analogy for this? Suppose it okay, so let's say we have to um, what can I give you? I need to give you an example to explain my concept over here. Um, so suppose you have to move from point A to point B, and the options are you can have a bus, right, which can take all the people from one point A to point B, and but the bus is slow. But and then we have a car which cannot take you from point A to point B, but which cannot take all the people from point A to point B, but can take, say, only 4 people from point A to point B. So and you have to transfer a lot of people. So the better idea was to go through the bus, because if you're going to take 4 people at a time from one to point A to point B, so you know that the car is fast, but it cannot take every people from one place to another place. And so if you have some time limit to go from one place to another place, so then it would be better to just have the car. This example is going to tell you that sometimes when you say that, okay, no, we can have the bus and the car together, this is not going to help you out, right? So
So
if you have
speed
if you
will be
have
same, but it's all about storage. Car has lesser storage as compared to bus.
yeah, car has
So
lesser storage, but it has got high speed. So you cannot use car and bus and say that, okay, so this is going to help us. This is totally a different example, right? So normally what you have, what I'm saying is that if there is in a normal life, if we have got a slow thing, and we add something more in between that, it's going to make the whole process even slower. Instead of making it faster, it's going to, because if there were 100 people to be transferred and the car is just taking 4 people, even though it's faster, but it's only taking 4, right? So if you say we have a bus and a car as well, so some of them are going to go from car and some of them are going to go from bus. This example is not going to work, because if you have to transfer from one place to another, it would have been better if you just have gone for the bus, because it's going to take all the people at one time, right? So the same thing over here, that we have got 3 levels. The third level was sufficient because it was containing all the data. So CPU could have used or only the third level, right? But it's slow, but it's still working. Now, but the early example that I gave you for the car is not going to work over here, or you can say this example is going to be different. So what's the difference in the program? What's the difference that the program exhibit that a normal example cannot exhibit? So there is something different in the program, and that thing is that the program don't access their elements randomly, right? So that's the main thing. That's the main thing that you have to consider, that whenever there is a program running, that program is not a random accessing program. Now that changes the whole thing. That concept that the program is going to access this element, is going to access this element in some kind of fashion, in some kind of determined way. This whole concept is then going to change how we design a memory system. So the basic idea is the programs don't access their elements randomly. They access them in a localized way. That is, all those references which are generated are going to be localized. Localized means that if you have accessed something, then the next reference is also probably from that same place, close to it. Okay, so that's the localization. So if the program exhibit localization. This means that if you need some data, then there are high chances that the next data element is also going to be coming from the same place. Okay, so then what you do is fetch a block of data instead of single word from the slower level. So even though it's a slower level, it's going to take this much amount of time once, but next time you will have your data available. Okay, so okay, the my are you getting my voice? I think so.
Yes.
The video is pausing. I think so. Some issue with my laptop from yesterday.
It
Okay.
is okay, sir.
Okay, it's okay. So
It's
so
fine, sir.
what I was saying was that um, uh, if we have a particular behavior from the program side, that they are going to access the elements in a localized way. This means that if you are accessing some point over here, then for a particular time all of your references are going to be for this particular from this particular area in memory. So if you have accessed one word, and for a particular number of times, you are always going to access some of the words which are going to be from this area of memory, why not bring this whole thing into the faster level, right? And then why not bring that part in the first level? Now this is how, if you are going to take the more time for the first access, but later accesses are going, because of this property of the program. Remember, it's a unique property. You cannot give that example for any other thing, because the programs behave in this way. The transportation example that I give you, that never had this experience, that we are going to go with some kind of a localized people, and then only these people have to be transferred earlier, or they need further that is going to be a different example. So if the CPU is going to access this a single word, and the next time the CPU is going to generate another access, but that is also already brought in to that first level, and the third axis is also there in the first level, then the first axis is going to take more time. Then what's happening over here? My laptop is behaving a little different way today. Okay, so the first axis is going to take this much time, but the second axis is just going to take t1 time. The third axis is also going to take t1 time, because your remaining axes have got some kind of you can say locality of reference. So there is this term is that the references are localized. So we call that as locality of reference, and this is the behavior of the program. So if the programs exhibit such behavior, then only we can have a benefit from a memory hierarchy. Now let's just assume our programs were random. Okay, so they are not random, but let's suppose they access their elements randomly. That is, after first instruction you jump to the to the 10th instruction, then you jump to the 100th instruction, then you come back to the 70th instruction. Now let's say if our programs were behaving in this way, then what would have happened? Then every time we would have accessed some element, we couldn't have find it. We couldn't have a we couldn't have found that element in our first level, right? Because it's going to be randomly accessing elements, and then each time you go for an element, you cannot find that in the first level, and this is going to be a problem, right? So this is going to be a problem for this whole concept. But this concept of hierarchy works because our programs behave in such a way. So our programs have some kind of locality of reference. That's the main thing, right? So I hope that that is clear. So the programs have both temporal and spatial locality. So when you're talking about a spatial locality, which we mean about space, so references which are then to a particular location, then the next reference to that thing would be a close reference from the previous. Like for example, if you want to add a constant to an array element, all the elements of the array, so you want to add some constant, so a program written for that would be working some kind of a loop or even in parallel. So you are going to add a constant value to every element. So the first element you're going to fetch, the next element is going to be close to it, the next element is going to be close to it, right? So that's called a spatial locality. That for example, the first element is at location 1000, then the second would be at 1001, the third would be 1002, right? So once you have accessed 1000 and you have added a constant to that level, the second element you have to access is 1001, right? So it can't be that there is a randomly accessing data and it's spread out on the memory. If that would be the case, then you are not even going to get any benefit from the memory hierarchy system. So that memory hierarchy system is only going to work because programs behave in such a way that they access their elements in a localized manner, right? So temporal locality means that if you have accessed something, it's more likely that you are going to access that again, right? So because of loops in our program, because that certain elements that are run again and again, so the programs exhibit both temporal and spatial locality. And because of this concept, what happens is that we can have our most useful or mostly referred items from the third. We can bring those elements from the third level into the fast level. And if most of the time we are going to access the faster level, then our overall average access time is going to be closer to T1 than T3, right? So you can say that average access time can never be lower than T1, or it can't be equal to even T1, because the first access that you have done is a very slow access. But when you're talking about average access time, you're going to talk about average. So if some of them are just taking T1 and some of them are taking T2, and a very few amount of them are taking T3 plus T2 plus T1, then this means your average is mostly going to be closer to T1, because most of your accesses are satisfied in the first level. And this is the concept over here. And this concept works because programs behave in such a way that they exhibit locality of reference, right? So is this thing clear now? So normally, if you're going to add some more level to something, that is always going to make that slow. If there was something there and you have added another level in between that, it's always going to make things slow. But this is not going to make it slow, it's going to make it fast, because programs behave in such a way that they exhibit locality of reference. So instead of bringing one word, we bring in a whole block of data, which is going to take less time to transfer than a normal, because in memories, there is another concept, which is that if you're going to transfer one element, it's going to take some time. But if you're going to bring in a block of data from that same memory, that time is not going to be multiplied by some factor. Like for example, if I need 100 elements from T3 and each time it's going to take T3 time, then I would say that 100 elements should take T3 into 100 time, right? But this is not the case. If one element takes T3 time, then 100 elements don't take 100 into T3 times. No. Whenever we are talking about memories, if you're going to transfer a block, that block transfer is quite fast. So it's not equivalent to 100 in T3, it's always less than this time. Why? Because only the first time you're going to go to that location, and since it's a block transfer, the next time you're just going to fetch the sequential data. And it's quite fast in all these memories. The block transfers are there. If you're talking about magnetic memories, like hard disk, the block transfers there are also fast. If you're talking about semiconductor memories, there also the block transfer is fast, because once the address is decoded, you reach a particular position, and then in each cycle you just transfer the data. You don't decode anymore. Because in any of the address transfers, the address is provided and it's being decoded. You reach that position. That that whole decoding takes a lot amount of time. But if you're talking about a block transfer, the coding is just done just once, and then the remaining cycles are reserved for transfers. So once you reach that position, you're not going to jump to any other position. So you just keep on transferring data. So block transfers are quite fast. So the idea is that if you have accessed a word, don't just fetch that word, fetch a whole block of data, and that would be much faster than individually fetching one word at a time. So 100 transfers are not going to take 100 transfers individually. The block transfers are much faster. So that helps us and reduces the time. And the other concept is that because the next references are also going to lie within that particular block, so next time you don't have to refer to T3 again. So and then again a part of that is going to go into the first level. And then if most of the time you're going to access T1, then the average is going to be more tilted towards T1 than to the higher level. I hope that is clear now, right? Okay. Is this thing clear now? Any questions here? Okay. So when you're talking, when you said that you need your significant data to be in the first level, this was just lacking one thing, that why means that why are we having significant data in our first level. So the thing is that programs behave in this way, that if they are accessing, and they tend to behave in this way, that they access a small amount of memory many times. So that's our significant data. So this is another property of the program, that they have a code which is referred more than than other codes. And then so you can get that thing also in the memory. And so it's all about the behavior of the programming. Any other example is not going to give you the same result. So when you're talking about the different computers, you see here that their hierarchies are also different. When you're talking about the personal mobile devices, you see that they have fewer levels of caches. So there are just two levels of caches here. We have level 1 cache and level 2 cache. The storage space is mostly flash memory, right? Uh, and then it's something in gigabytes, right? And then we have memory, the you can say the RAM that you are going to refer to. It's around 1 to 2 GB. It has changed now, 4 GB up till here. So personal mobile devices are varying in their capacities, and there is a demand for more and more. But the number of levels are reduced because they are powered by battery, and so you cannot have a very um, big memory hierarchy, and you cannot have more levels, because you see here that this L1 cache has to be small, because if it's going to be big, then it's going to take a lot of power. That's another reason this technology is fast, but it takes a lot of power if you implement more of it. So you're going to see in most of these design, this first level cache has to be small, and this is then going to save both power and your cost. When you're talking about memory hierarchy for laptops, you see here the storage space previously was magnetic, but now it has changed to flash drives. Again, solid state devices. Solid state means that your bits are stored as ones and zero in some electronic device, some capacitive devices. So there are uh, devices which are made through silicon, that are storing the ones and zeros in forms of capacitive values. And then so they are called as solid state devices. There are other options still, like hard disk of magnetic medium, but that is quickly changing. And the other reason why, because it's you need those laptops to be portable. And if you have got any mechanical system in your laptop and you want to move it from one place to another, that mechanical system easily gets disturbed. And this is the main reason why many magnetic disks are also crashed. Also crash when you move it from one place to another while they are on. So that is a little problem. So that's why the main storage has changed from magnetic to flash memories even in this case. So the problem with flash, if you compare it with RAM, is that it's slow. So you can see the time here, that's in microseconds. And for time of the RAM, the random access memory, that's again you can have a dynamic DRAM, or you can have a static RAM. So and static RAM is even faster. Mostly these levels are designed through static RAM, but the DRAMs are have more capacity. So they have a different technology which is slower, but it gives you um, a very small size for a particular bit. So that means that you can have more capacities, but you need refresh rates, and you need to refresh it on and on. So it's also volatile. If you go for servers, you're going to see still there are disk storages, magnetic mediums implemented over here, which are having high capacities but also very large amount of time to access data. Okay, so normally you're going to see that in all these different types of computers, there are always levels of memory. So it's not that CPU is directly accessing the RAM, which is getting data from the storage. There are different levels in between, and these levels help, right? So we are going to come to that, why do these levels help, and how to find the average access time. We are going to come to that shortly.
So can we manipulate the speed, or this is predefined?
Can we what?
Manipulate the speed, which is mentioned in this slide.
Manipulated by how?
Is it possible to manipulate the speed or latency, or it is a predefined, it's fixed?
No, it's not fixed. I mean, this slide has been taken from the book, which is a 2018 edition. But this technology has changed a lot, right? So this is changing continuously. So some of them is not changing. Some of them, like for example, RAMs, you are not getting better speeds for RAMs, better capacities for RAMs. But for Flash, it's changing a lot, right? For Flash, they are reducing the delays of
And
access
sir,
the Flash.
the number of cache levels, it is fixed that
Yeah,
there will
cache
be three
levels.
cache, or it can be more in
That can
with respect to
that can
laptop
be
and
more.
desktop.
That can be more as well. But normally, you are going to find that you it's going to take more power if you're going to have a third level in a mobile device.
So
So
in case of mobile device, nowadays there are mobiles coming that 5,000 ampere or larger power. So that it's mean that they have more cache level.
they can have, but normally these batteries, when they are going to increase their capacity, it's not because they want to have more cache levels. It's because they need more time, they need more standby time, or something like you need the user to feel convenient without if you are having two levels and they are okay with the speed with for that, then there is no reason to have a third level in there, because more levels means uh, you need to take care of where should that level be implemented. That's going to take more power, right? And there won't be much benefits for that, right? Anyhow, but these systems are moving. So they are going to be different designs, right? So it's not obviously fixed that you cannot have any mobile device which has got just which cannot have three levels. They can be three levels as well, but normally the better thing is to have fewer levels in a mobile device. Then the laptops and desktops, and even their sizes are going to vary. Their cache sizes are also going to vary depending on how they are going to access it. Their memory sizes are also going to vary. Now we are going to come to that as well, because this is not only about sizes, it's also about power. So if you have got a higher memory, if higher capacity memory, um, if you implement a faster memory and you increase the size of that memory, the faster memory is going to take a lot of power. So if you increase the size of that power is not going to change linearly, it's going to change exponentially. And when it changes exponentially, this means the battery is going to consume a lot of power. And it's not only about power, it's about heat as well. So you need to dissipate that heat, because otherwise the whole system is going to burn out, right? And so this heat has to be dissipated from the system, so you have to remove that heat as well. So that is easily done when you're talking about desktops and servers. But for personal mobile devices, if your system gets heat up, and then it's going to destroy the whole thing, and even though you cannot carry it as well, right? So there are different things that have to be taken into consideration while designing the memory hierarchy. So normally there are levels, and then their capacities have to be adjusted as well, so that they don't really affect the user. But these maximum values obviously are not really fixed. You can see systems which have got different capacities. Like for example, 64 GB. Today we have systems which are having even 256 GBs for a person, for a mobile device as well, right? So these things are changing. Storage capacity is shown over here for desktop to be 2 terabytes, but you can have more than that as well these days, right? So obviously this thing is just one typical uh, configuration for laptops, desktops, and personal mobile devices. Okay. The main idea is that every computer is going to have different levels of memory, and these levels have different speeds and sizes, right? So everyone is built using a different technology. So level 1 cache has a different technology, level 2 cache has a different technology. Then there are some caches nowadays that are built within the chip, right? So level 1 is mostly within the chip, and then within the chip there are different technologies, right? So how to stack those chips, that's another technology. So having vertical stacking is a different technology, and then you can build that in a different way. So all of that matters. So that thing obviously cannot be explained in the one slide, but all of this is going to is also changing, and then you can see different varieties over there in the existing mobile devices, right? Okay, so if you talk about the performance, memory performance gap, we have looked at that as well in our first lecture. When we talk about performance of memory and processor, we see that there is a big gap. That gap wasn't much when we're talking about 1980s, because uh, processor were not very efficient at that time, you can say. And or you can say that the memories were quite efficient and they could provide the data whatever was wanted by the processor, right? But then processors kept on advancing, and when they kept on advancing, their performance increased manifold. But the memory technologies could not uh, these memory technology could not improve at the same rate, right? And so we see here that mostly it's linear for memories. If you're talking about from 1980 to 2015, that their performance, so it's a log graph as well. So you can see here that the technology for memory has improved, but the technology for processors has improved manifold. So if you are improving the memory technology from 1980 to 2015 by 10 times, you see the same thing has improved from 1980 to 2003, something like 10,000 times for the processor. So the demand from the processor side has increased a lot. So there are the processors are getting very advanced, and they want to access more amount of data. They want to access more and more amount of data, but the memory cannot provide the same amount of data. So that's the main thing. the memory is lagging behind. So that's the memory performance gap. And you can see that even after 2003, when we moved to multi-core system where there are many cores providing data, so each core has can have its own memory as well. So if you're talking about a single core, you're going to see that at this point the frequency of the cycle was not increased anymore, and then more and more work was done on multi-core systems. So if you're talking about a single processor, for a single processor, this diagram is for a single processor. So the single processor has somehow the performance of single processor has not improved a lot from 2003 onward because of multi-core systems where we were talking about getting performance improvement through parallel processing. But the memory demand has also not memory capacity has also memory you can say performance has also not increased a lot. So there is still a gap, and that gap is a lot big gap because this is a log graph showing over here. So you can see the 10 and 10,000 is quite a big difference, right? So in other words, we can what we can say from these systems today is that the peak demand of a processor has increased a lot. So let's take an example. So the aggregate peak bandwidth grows with number of cores. So this is also an older example because these days we have got much advanced systems now. So Intel Core i7 has got 4 cores running at 3.2 gigahertz, right? Let's take an example. So we have got 4 cores, right, for i7, and then each core is running at 3.2 gigahertz. So every core can generate 2 data memory references per core per cycle, right? So every core can generate 2 memory data references per cycle, which means that there are going to be 25.6 billion 64-bit data references per second because every reference is for a double precision number. So there are going to be 25.6 billion data references per second if you're talking about all the 4 cores. Additionally, in the same cycle, 128-bit instruction references per core per clock can also be generated. So this means an additional 12.8 billion references, which means that the total demand from the processor side is something like 409.6 gigabytes per second, right? So what you're talking about is the processor wants this much amount of data per second. This is the peak, right? So this is a peak that processor can demand from memory. The processor needs its memory to supply it with 409.6 gigabytes per second, right? But the memories have not kept pace with that, and the DRAM can only provide up to 8%, that is 34.1 gigabytes per second, right? So 8% can be handled by DRAM. So this means that DRAMs are not enough. This means that the technology of DRAM is not going to go because it can only provide you 8% of those demands. So either the processor stop its demand and then the DRAM can satisfy it, or it's going to wait a lot. Okay. So for that, if we need to handle such a demand, we need multi-port pipeline caches, separate first and different levels of caches per core, and we also need separate instruction and data caches at the first level so that we can handle those instruction references separately than data references, like a Harvard architecture that we discussed earlier, right? Okay, so this was about the peak demand and what the memory can supply. And so what we need to overcome this, we need multi-port caches, different caches, and we need pipeline caches. So they work in their pipelines, means that their process is also pipeline. So it's not going to take the whole one lump sum amount of cycle, but their task has also been divided into stages, and then you can work through accessing of data. Multiple references are going to run parallel, right? And different levels of caches and different instruction and data caches. Any questions here? Okay. So if you look at the performance, memory power and performance, you're going to see that if you're talking about so this graph here shows the how the latency and the power is going to change if you're going to change the size of the memory, right? So if we are talking about one particular technology, so if the memory size is 64 bytes, then its latency is something measured over here in terms of nanoseconds, and then this purple graph here shows the energy in nanojoules. Now you can see as the size increases, the latency increases linearly, almost linearly. But when you're talking about the the energy, you're going to see that after 8K, after the memory size reaches 8K, adding more to that, doubling that size, 16K or 32K, means that the energy required for that memory uh, is going to grow exponentially. So it's not linear anymore, it's going to grow exponentially. So this means you cannot have memory sizes of any sizes that you want. These sizes have to be adjusted according to that technology, where that memory level does not have an exponential growth in its power consumption. Okay, so this means that the sizes of the memory, the first level, the fastest level memories have to be small as well. And in the personal mobile devices, about 50% of the total power consumption is about 25 to 50% of total power consumptions are done by the caches itself. So caches have to be very optimized, because if you have more caches, or if you have a hierarchy which is not working perfectly, then you're going to see that it's going to consume a lot of power. And if the mobile device's power is leaking a lot, this means that users are not going to be satisfied with that, right? So these are all the issues that have to be dealt with. So now I'm going to come to some of the existing terms that you have studied, and I'm just going to give you an overview. But before that, let's have some questions if there are any. So today's topic would be more on an overview of what we have done earlier and some new topics that we are going to study. Yes, Yasir.
So that's why whenever we see any default configuration of any desktop or laptop or any other server, there is very less RAM or memory. And reason
Uh,
behind this that it will, if we go for higher memory or higher RAM, it will consume more power.
no, and if you're talking about desktop and servers, they really don't concerned about power. So the reason for that is cost. In the case that you have mentioned, the reason for that is cost, because the manufacturers have to sell their system, and they know that the consumers, they can uh, they can add more if they want, but they need the price which is less. So whenever they are going to give you some default configuration, they are only always going to give you what's best for a particular level of satisfaction, and then it's also cost less, so that the consumer also can buy that easily. Because if they are going to increase their cost, then the consumer is going to take a cheap thing, and that's going to harm them, because they are going to be obviously cheaper models in the market. So what they
Okay.
do is they go with a default configuration with less amount of RAMs and different other configurations that they can change. And if you want to add more, then they give you options to add that as well. So that's not a big problem. But they're not concerned with power. When you're talking about systems where the mobile systems, that cannot be changed. So they have to come with pre-configured models. So then they go with different models altogether. So then they have different options. So they go with 32 GB RAM as a separate thing, and a 64 GB as a separate thing ROM. So then they have different models that their fixed ROMs have different models, and so again they use a different memory for that system as well. So their memories also change because they know that increasing the RAM or ROM size is going to affect the memory. So they have a different battery as well over there, right? And then they sell that at different price. They sell that at higher price. So all is this because of consumer satisfaction, and there is a lot of research done on that. And then that's not part of this course, but whenever you're going to design something, one part of that is for the engineers part, the other part is about the selling part, the marketing part, and then there is a lot of research on that, how what the consumer wants, and how to satisfy that, and how to fool him as well, right? So you can easily fool them, how you can easily fool them to buy your thing. So the main thing is you need to sell your things, right? So if you want to sell their things, and if it's a good thing but users are not going to buy that, then it's useless for you. So you need to sell that, to give them different options, and they are going to select that option whichever the suits better for them, because not everyone can purchase a high-end model, even though they know that a high-end model is going to be fast, but not everyone can do that. So they build different models for different configurations, and then different battery sizes to satisfy those configurations, right?
Okay, sir.
Okay, so let's go with some overviews before I come to the main topic of caches and how to optimize caches. So these are terms that you must have studied earlier. So when we're talking about a memory hierarchy, these are very common terms. Like when a word is not found in the cache, we call that as a miss, right? So if there is a miss, what we do is we fetch the word from a lower level of hierarchy. And we call that as the lower level because the higher level is the one which is closer to the CPU. Okay. And obviously lower level has got high latency, so it's going to give you that same word in more amount of time. So lower level may be another cache, the main memory also. And when we are going to fetch a word, we don't fetch only a single word, we fetch a whole block of words, because we need to take advantage of the special locality, as we have discussed earlier. Now, these are terms that are specific to cache. So when you have different sizes of memory, this means that you cannot have everything within that memory. So to be simple, I'm going to talk about just two levels. So we have a CPU, and we have a cache, and we have a main memory. So let's say this main memory has got everything, and this cache has got can only hold a subset of the data. So if only a subset of data can be stored over here, because the size is not equivalent to main memory, this means that you cannot hold everything which is in the main memory in the cache. So if you're going to store a subset of that, and the CPU addresses are actually the addresses of main memory, because if the CPU is generating something, like if the main memory has got, say, um, how much, say, let's just take an example, 1024 locations. So for 1024 locations, the CPU needs a 10-bit address. So CPU generates a 10-bit address, but that address is for main memory. So in between, then there is a cache which is going to check whether that data is there. Now, the first thing that comes to mind is, if the cache cannot hold everything, then there should be some way of mapping in which we can put any particular data from memory into cache. So there should be some way of doing that, some mapping to map a data to a particular place. So for example, if something has to come from this point of main memory into cache, it's going to go over here. So there should be some mechanism to do that, some mapping functions for that. That if because their sizes are different, you cannot have everything in memory in cache. So this means that there needs to be some mechanism for dealing with that. Okay, so a block placed into cache in any location within its set determined by its address. So block address mod number of sets is going to tell you where that particular block is going to be placed. I'm going to come to that when I'm going to discuss the mapping, right? But there needs to be some mechanism for storing the data in the cache. Now miss rate, so the fraction of accesses that are not satisfied within the cache are then going to be called as miss rate, right? And the opposite would be the hit rate. So the fraction of accesses that are satisfied in the cache that you can find in the cache are then going to be called as the hit rate of that cache. Now, what are the causes of misses? There are three causes. One is called the compulsory miss. So in a compulsory miss, what happens is that you always are going to you experience this miss because this is the miss when you are going to power on the system or bring the block for the very first time in the cache. So the first access to any particular word is always going to be a miss because it's not going to be found in the cache. So you are going to access that block, and the very first access to a block obviously is not going to be there in the cache. So that's something that is acceptable because that's the very first access. So we call that as a compulsory miss, and that's always going to be there. Okay. Then there is a capacity miss. So if the cache cannot contain all the blocks needed because of its size, then we are going to say that and if you want to so if you have accessed a block and you have accessed that first time, that would be called as a compulsory, and you cannot find that in the cache, that's going to be called as a compulsory miss because that's the first access. So you're going to bring in that block, but once the block is there in the cache, any other miss after that would be different than compulsory miss, right? So what happens is, because the cache has got limited storage, sometimes you have to throw that block out of that cache to make space for some useful data, some useful blocks. But what happens if you need that same block that you have thrown out again? Okay, now the reason for throwing out that block can be different. One reason can be that you cannot store that block because the size of the cache is not enough to store it, to keep that in the cache. So that would be called as a capacity miss. So the second time you have accessed that block and you have not found that in the cache cannot be called as a compulsory miss. That is either a capacity miss or a conflict miss. And if you have thrown that block out because the cache cannot contain that block because of its capacity, then that would be called as a capacity miss. And if you have thrown that block out because of your mapping scheme, which don't allow two blocks to be stored together, coming from one place, coming from different places from of memory into a single place in cache, that is called as a conflict miss. So there is a conflict of a set. So you bring in that block in a set, but then you need another block which also is mapped to the same set. So because the set can contain only one, so you have to throw any one of them out. So since you need that later one, so you're going to throw out the earlier one. But if you need that earlier one again, so since you have thrown that out and you cannot find it in the cache, that would be called as a miss. But that miss cannot be compulsory miss because you have already brought that into the cache once. So the compulsory miss is only the first time. But the next time and the third time, it's going to be either capacity miss or conflict miss, because since you have brought that into the cache, why can't you find it again in the cache? So if you have thrown that out from the cache because of capacity, that would be called as a capacity miss. And if you have thrown that out from the cache because the set cannot store both of these blocks simultaneously, that would be called as a conflict miss. Okay, right? So these are three different misses, but if you increase the capacity, obviously you can reduce the capacity. Means if you have more associative cache, if you increase the associativity of the cache, in other words, then you are also going to reduce the conflict misses. Okay, so we have already gone through that CPU execution time earlier in the first lecture, but here we are going to now introduce the memory stalls as well. Previously, there was CPU cycle time into clock cycle time, and that was our CPU execution time. Now we are going to talk about CPU cycle time, clock cycles, plus memory stall cycles multiplied by clock cycle time. That's going to be our CPU execution time. So when you're talking about CPU execution time, you're also going to consider the stalls required, the delays required due to memory, right? So our memory stall cycles are number of misses multiplied miss penalty. So if you have a memory stall, it's the number of cycles, memory stall cycles required over here are going to be equal to number of misses, the number of misses that you have occurred, and what is the penalty in terms of cycles of each miss. For example, if every miss requires 25 cycles to get that data, then the miss penalty is 25. And if there are total 1,000 misses in your program, then 1,025 means 25,000 cycles have been lost. So 25,000 cycles have to be included into CPU execution time, because that's something that has to be considered when you're talking about the CPU execution, right? So number of misses can then be defined in other terms. That number of misses means how many misses. Like for example, if I said 1,000 misses, so how did I get to 1,000 misses? So this means there is a miss rate as well, misses per instruction. So what is the miss rate and what is your instruction count? So if the miss rate is 1%, right, and the number of the instruction count was, say, something like a million, so then 1% of a million would be just 1,000. No, say 100,000. So if your instruction count was 100,000, then 1% of instruction count would be just 1,000. So that's how you get number of misses. So instruction count into misses per instruction. But then the main thing is, how are you going to find the misses per instructions, right? Because this is then the question mark thing. So we define misses per instruction as memory accesses per instruction into miss rate. How many memory accesses have occurred per instruction, and what is the miss rate of those particular elements. So misses per instruction are defined as memory access per instruction into miss rate. So that is again more defined form, and this is going to give you better results for memory cycle stall cycle. So if you know what is the instruction count, and you know how many instructions are accessing memory, and then you know what is the miss rate of memory, and then you know what is the miss penalty, then you can find out the memory stall cycles, right? Okay, so again, this is an approximation, because this miss rate is going to be different for reads and writes. Sometimes memory reads have less miss rate than memory writes, and the miss penalty also is different, because the reads miss penalty is a little different than writes miss penalty. So if you want to be more specific, then you can write the same thing as instruction counts into reads per instructions into read miss rate into read miss penalty plus instruction count into writes per instruction into write miss rate into write miss penalty. That's the best formula. But in this formula, what you need is a read miss rate and a write miss rate. So if you have the read miss penalty, write miss penalty, read miss rate, write miss rate with you, then if your program has got 10,000 instruction or 100,000 instructions, reads per instruction, how many reads per instructions are going to be there? There is always going to be one read per instruction, because instruction is going to be fetched. So fetch is a read operation, right? So there's always going to be one read per instruction. But then there could be some load instructions as well, When you have load instructions in your program, that means your number of reads are going to increase. Writes per instruction, only store instructions are going to write. If you're talking about a MIPS processor, only store instructions can write to the memory. So number of store instructions are going to tell you how many writes per instructions are going to be there. So if there are just 20% store instructions in the whole program, then 20% of 100,000 would be how much would that be? 20,000. So 20,000 writes would be there, right? And then so writes per instruction would be then a fraction, right? So you can calculate that yourself. So let's take a question here. Let's take a question here. So assume we have a computer where the cycle per instruction is 2 when all memory accesses hit in the cache. The only data accesses are loads and store, and in total they constitute 50% of the instructions. If the miss penalty is 25 clock cycles and the miss rate is 2%, how much faster would the computer be if all references were cache hit? Now I will give you some time to read this question yourself to see what you have understood. Okay, so what do we want to know in this question? So that last part here says that how much faster would the computer be if all references were cache hit? And then it says here that if all references are cache hit, then the CPI is 2. This means that if we can find out what the new CPI is, if the references are not cache hits, then we can just compare their CPIs, and you cannot go below 2 because this is the best CPI, because this is for when all memory accesses hit in the cache. So if all memory accesses hit in the cache, this means there is no miss penalty, right? There is no delay. There is no penalty of 25 clock cycle because every reference is there. So if that is the case, the maximum CPI that we can have is 2. The best CPI, not the maximum. The best CPI that we can have is 2. So, but we need to find out what should be the CPI if there are 50% loads and store and the miss penalty is 25 and the miss rate is 2. So it says that for 50% instruction, 2% of those instructions are not going to be found in the cache. And if they are not going to be found in the cache, then each one of them is going to take 25 clock cycles to be fetched and be put in the cache, and then you can access that, right? So first of all, what is 2% of 50%, right? So that's going to give you how many instructions are actually going to incur a 25 clock cycle penalty. So let's go through that. So the easier part is always to find what would be the CPU execution time if we say that our cache is always hit. It's because you have to compare that. So CPU execution time is instruction count into CPI plus memory stall cycles into clock cycle time. So since the memory stall cycles are 0 in this case, so we get a CPU execution time as instruction count because there is no instruction count defined over here. So we are going to take that as instruction count. So instruction count into 2 into clock cycle time. So that's the best thing that we can have, because clock cycle time is also not given. So since we have to compare it, so we need to have some figure. So we have defined that. Now what is going to happen in a real cache? In a real cache, we have the memory stall cycles. So we have defined that in the last slide. The memory stall cycles are instruction counts plus the memory references per instruction into the miss rate into the miss penalty. So what is the memory references per instructions? So what is the memory reference per instruction? So we have got every instruction which is accessing the memory once, and then there are 50% 50% of the instruction which are accessing the memory twice. Okay, so every one of them is accessing the memory once, and then there are 50% of them which are accessing the memory twice. So that would give you a 1 plus 0.5, right? So 50% of the instructions are accessing the memory twice, and 100% of them are accessing the memory just once, right? So that is going to give you the number of memory references per instruction. So per instruction, the references are going to be 1.5. Okay, is this thing clear? Because that's the main part where the students are a little confused. How do we get this 1 plus 0.5? So if we go back to our previous slide, we have this formula. Memory stall cycles is equals to instruction count multiply memory accesses per instruction multiply miss rate multiply miss penalty. Now memory accesses per instructions mean how many accesses are happening per instruction which are going to the memory. So you know that every instruction is going to have a fetch stage. This means that every instruction is going to fetch the memory. Every instruction is going to be fetched from the memory. This means there is at least one memory reference per instruction. But then 50% of the instructions are also going to go through the memory stage, which means for 50% instruction there would be two references. So for 50% there would be one reference, and for 50% there would be two references. So what's the average? The average would be 1.5. So 1.5 references per instruction, that's the average. So that is what is written over here. So we have got 1.5 multiplied with the miss rate, which is 2%, so 0.02, and the clock cycle time is 25. So this is going to give you the memory stall cycles, which are going to be 0.75 into instruction count. And we can put that in the same formula for determining the stall cycles here. So then we can add that together, and then we get 2.75, and then you can compare them. So you're going to get the speed up 2.75 divided by 2, which would be how much? 1.375. So if all the references are hit in the cache, then it's going to be 1.375 times faster than a real cache. Okay? Any questions on this? Any questions on this? No? Are you people getting this? Because you're not asking.
It needs practice a bit more, but once I do practice, it will be much more clear.
Yeah, but I'm not getting any questions today because memory hierarchy is a topic which you have studied earlier. I mean, all of you might have studied that in an undergraduate course. Isn't that true? So you are familiar with these terms of miss rates and hit rates and instruction counts and other things, because now we are going to go with some cache optimizations today. Okay, for this problem, you can go through that yourself too, and if you still find any problem, then you can ask me in the next class.
Sure,
right? But it's an easy thing, but maybe you're doing it for the first time and then you are not getting the right terms here. So I'm going to start with my remaining topics. So again, something which you have studied earlier. So when you are designing a memory hierarchy, there are four important questions that come into your mind, because you see that there is a memory which is a bigger size, and then you see a memory which is a small size, right? And then you also see that CPUs are always accessing the memory which is of small size. So the first question that comes to mind is, where can a block be placed in the upper level, right? So if you want to bring something from a bigger memory into a smaller memory, where should that be placed? Okay. And if there is a block in that smaller level or upper level, how to find that block, right? And because the sizes are different, so you cannot have everything in that smaller memory. So if you need to replace something, which block should be replaced? That's the third question. And the fourth question is, what happens on a write? Why is this question important? Because we say that a smaller level is always going to keep a copy of the bigger level. So if you do a write operation, how are you going to handle that? Are you going to write only in the small level, or you're going to write on both the levels? Because if you are not going to write to both the levels, then the copy is not the same, right? So these are the four common questions that come to mind, and we are going to address all of these questions one by one, right? So the first question is, where can a block be placed in the upper level? So there are different schemes for placing the block, and these are the mapping schemes that that I was just alluding to in the previous slides. That there should be some mapping because we need to have some way of knowing or placing a block. So there are three different mapping schemes: direct mapping, fully associative, and set associative. I'm sure every one of you are familiar with this. Is anyone here which who has not studied these mapping schemes? Direct mapping, fully associative, set associative, because these are part of your main course here. So you have not studied anything related to that in your undergraduate course? I'll say that.
Yes, sir.
You have not studied direct mapping, fully associative, and set associative. You have not studied caches.
No. No. Anyone with
Okay,
caches in
because
undergraduate. All, we have a basic architecture, but how to perform arithmetic in LU and
okay,
design
okay,
LU.
okay. So one thing that
Morris Manu book, maybe.
okay, so one thing that was different from you people was that uh, your admission process was a little different, because normally what we do is we take interview of the students, and we see what the student has studied or what he has not studied, and then according to that we suggest some non-credit courses to the student. So any student who has not taken computer architecture, computer organization or architecture in an undergraduate level is normally given a non-credit course of computer architecture in computer organization and architecture course in the master's level. But since that was not your case, so you have to do that yourself then, right? Because you cannot take another course now. So yeah,
Inshallah, sir.
try to keep up with the pace. Okay, so when you're talking about mapping scheme, so here at the bottom you can see here this is a memory shown over here, right? So let's say we have a memory which has a capacity of 32 words, right? I'm going to talk about words here. So the memory can hold 32 words, okay, or let's say blocks, okay. So not words, blocks, because a word would be a little too specific here. Okay, so I'm going to first of all define these things. Now, word is normally the smallest unit or an addressable unit that a CPU can address. So word can have different sizes, it's not fixed. So it's not like a byte or a bit size which is fixed. Word can have different sizes. So you can see here that some of the processors have word size of 32, some of them have word size of 16, some of them have word size of 8, and some of them have word size even of 64. So word size is different for different architectures. But word is something which is accessed as a single entity by the processor. Okay, so this is something that the processor needs. Then a collection of these words are going to form a block. So let's say if we have got 4 words block, then this can be called as one block. Again, this term of block hasn't got any fixed size. So if there are 4 words in a block, you can say it's a 4-word block, but then you can have an 8-word block as well. You can have a 64-bit block as well, 64 word block as well. So you can have any sizes of block, but block is a collection of words, right? And these are coming from the same locations, right? So they are not randomly selected and put into the block. there are contiguous locations. Okay, so whenever we bring something into from the higher level from the lower level to the higher level, we don't bring a single word, but we bring a whole block into that memory. Okay, now the first question is, where can we place that block into the memory? Now, in order to place that block into the cache, we need in cache spaces that can occupy the same thing, right? In other words, we can call that as a cache block. So we need a main memory block to be placed into a cache block, right? So we need both of them to be the same space because it has to come over here, right? It has to come over here. So the main memory block has to come into the cache block. Now, because these terms, main memory block and cache block, are a little confusing, if you keep on repeating them, then you get a little confused. What are you talking about, main memory or cache? So then we just say main memory block as block and cache block as line. Okay, so they are the same thing, but we have just changed the term to cache line to make it easy to understand, right? So now I'm going to come back to this diagram over here. So let's say this memory can hold 32 blocks, and we have a cache which can hold 8 blocks, right? So that means that this cache has got 8 lines. Okay, so a block is going to go to one line because they are the same thing. That we have just changed their term naming because to make it a little simpler. So one cache block can occupy one line. Okay, now let's go with the first scheme. Let's go with the first scheme, which is direct mapping, right? So in direct mapping, we need to find out if our block size is 12, we need to find out where can we place this 12 block in the cache. Okay, so what should be the best place to place this block in the cache? Now there should be some formula. In a direct mapping case, there is only one place to store this block, and that can be determined by a simple formula. Now, because there are 8 lines in the cache, what we do is we use a formula which is block number mod. Mod is a remainder operator, the modulus operator. Mod the number of lines in cache. Number of lines in cache or number of cache lines. So number of cache lines means, so for example, we have here 32 blocks and 8 cache lines, right? And you need to find out where is block number 12 going to go. So what you can do is, this is your block number 12, take the mod operator with 8. That's the remainder operator, means you need to find out what is the value as a remainder. So if you divide 12 by 8, what is the remainder that you're going to get? So 8 ones are 8 and you're going to get 4. So 4 is your answer here. So this means that 12th number block is going to go to the 4th line. Okay, so here 12th block is going to go to the 4th line. And likewise, you can do it for any block you need. For example, if I need to find out where is block number 15 going to go, so what would be your answer? Block number 15, anyone? Come on. Where is block number 15 going to go? 7. Okay, good. Anyone else? Why aren't you people speaking? 7. Okay, now it's good.
Seven,
Right,
seven,
right, right. Okay. So if I ask where is block number 4 going to go then?
4.
4. So this means that block number 4 is also going to go to uh, line number 4. And if I ask where is block number 20 going to go then? That's again going to be 4. And if I ask where is block number 28 going to go then? That's again going to be 4. Right?
Yes.
So there are 4 main memory blocks that can occupy one cache line. Right? That's the mapping between them, because all of them are going to give the same answer if you are going to go through this formula. The block number mod the number of cache lines. So my number of cache lines are 8 because you are talking about 4, 12, 20 and 28. All of them are going to give you answer 4, and this means these 4 blocks are going to come to the same line. Now the problem here is there is a single line. So if you need block number 12 and 20 at the same time, that is not possible in the cache. So only block number 12 can come, or 20 can come, or 28 can come, or block number 4 can come at one time, because they all are going to come in line number 4, and line number 4 can hold only one block. So this is the main thing in a direct map cache, which is a problem over here. When you're talking about fully associative cache, then the other scheme is to have to allow the blocks to go to any line they want. So it's not about a fixed line for a particular block. It's about if that line is, if the cache line is empty, then the block can go to that line, right? So there is no, in a fully associative cache, there is no fixed formula, right? So any block can go to any line, right? So block number 12 here, that is our desired block, can go to line number 0, or line number 1, or line number 2, or line number 3, or 4, or 5, or 6, or 7. So any line, if it's free, right? So all of them are shaded. So, but this means that it would be a little difficult to find that, but that's our second question. So in a fully associative cache, it can go anywhere in the cache. This block can go anywhere in the cache, okay? But then there is another mapping, which is a set associative mapping, in which we define a set. So a set is a collection of line. So set can be called as a group of line. So you combine and different lines in a set. So you can say a group of lines or a set of lines, cache lines. So when you define a set, what you do is you say that if you have a set, so if there are 8 lines, so if there are 8 lines in the cache, then if you define a set of consisting of 2 lines, then you say that this is one set, this is another set, this is another set, and this is another set. So this means then you have got 4 sets. Okay. Now a line, a main memory block is still going to go to one line of the cache, but that line is not defined. You define the set for that particular line, for that particular cache. So this means that there are now 4 different sets option, and within the set option, that particular block can go to any line which is free. So our formula changes a little bit over here. So our formula for determining which set is it going to go is block number. So I'm going to write that same thing over here then. So the formula would be block number. The previous formula for direct map was block number mod number of cache lines. Now it would be block number mod number of sets. Okay. So if we have defined that there is a two-way set associative cache, in a two-way set associative cache we have two lines per set. In a four-way set associative cache we have got four lines per set. So if we have defined there is a two-way set associative cache, then there are two lines per set, and this formula changes and we have block number mod, instead of number of cache lines we have number of sets, so which is 4. So we have block number mod 4. So we have to do it with 4 because that's our number of sets. So if you need to find out where is 12 going to go, you're going to take 12 mod 4, and that is going to give you 0. So this means it's going to go to set number 0, and within set number 0 there are two lines. So it can go to any line which is unoccupied. So if there is already a block over here and this is free, then it's going to come over here. But if there is a block over here and this one is free, then it's going to come over here, right? So if we come back, we see here that if you're talking about block number block number 12, then it can go to set number 0, which is identified over here. What's not identified is which line is it going to occupy, because both of them are shaded, which means it can go to any one of these lines. Okay, so I hope these three placement policies are clear. Our second question is, how is a block found in if it is in the cache? Now for the first for the direct map cache, it's very easy, because you have just one place for that particular block to be placed in the line, in the cache, and then it's easy to find it back, because you can only place it in that place, in that particular line, right? But in order to understand that, we need to first of all see how is a memory address interpreted by the cache. So the CPU is going to generate some address. That address is actually for the main memory, that this is the word address, right? When we're talking about interpreting that from the cache perspective, then cache divides this into three different fields. One of them is the tag field. Another one is the word field. Another word is the set or the line field. For direct map, it would be called as a line field. For set associative cache, it would be called as a set field. Now, as the name specifies, this is going to tell you which line is that block going to go, or which set is that block going to go. This is the word field, which means since the block has got multiple words, which word are you talking about from that block? Okay. And then there is a tag field. Now, tag field is something which is a little confusing for students, but tag is something which is identifying between those blocks which can come to the same line. Now, if I come back to the picture over here, the last thing that we described over here was in set associative cache, we saw that there are 4 different blocks which can come to the same line, right? So when we say there are 4 different blocks that can come to the same line, this means that there is a competition between 4 different blocks to occupy this line. Okay. So in other words, what we can say is, if there is something here in this particular line, it is either block 4 or 12 or 20 or 28. Okay. So since there are just 4 options, we can identify them by giving them a unique code. So we say this as 00, this as 01, this as 10, and this as 11. Right? Now, if we have this unique code along with this cache line, we could easily know which particular block is there. Right? So because now this is only a data storage, but for that we need extra storage. So let's say what I'm talking about is, if we have got some extra storage along with every cache line, which is holding a 2-bit code along with every line, then that 2-bit code can easily identify which particular block is over here. So for example, if that 2-bit code currently is, let me just clear something. So let's say we have this 2-bit code over here along with every line, and let's say this 2-bit code over here is 10. So 10 means that block number, or not 1001, this is written from the bottom to the top. So this means that yeah, right. So let's say if it's 01. Now 01 means that we are talking about this block over here. Right? So in order to identify which block is currently in the cache, we need some extra storage space in cache to hold that thing. Now that is a tag field. And tag is actually basically something which is going to identify uniquely which blocks can come over here. Okay, so this is defined over here. So if you're talking about address, it's defined as tag, index, and block offsets. So if you need to find any particular block, what you do is you, and this is your cache, for example. This is the data part of the cache. And then there is a corresponding address part or the tag fields within the cache. So every cache line has got an associative tag field as well. The same thing that I've mentioned. And within that block, there are different words. Okay. So what happens? How do we start? So first of all, this address is going to break this, the cache is going to break this address into 3 different fields. Now this set or line is going to first of all go to that particular line. So if there is a 00, if there is a 001 written over here, then it's going to go to line number 1. If there is a 100 written over here, then it's going to go to line number 4, and so on. Right? So the first thing that happens is it goes to that particular line. Then it matches the tag. So there is some tag stored along with that line, and then there is some tag coming from the address. So it matches those 2 tags. If the value is same, this is the same address that you want. If the values are different, this means this is not the same block that you want, which is currently in the cache. So you have to bring that in from the memory. You have to bring that block from the memory. So if the tags are cached, if the tags are matching, then what you do is use this word field to select one of those words from the memory, and you pass on this to the CPU. So this word is then passed on to the CPU, and this is how it works. So if it's matching, then it's okay, but if it's not matching, then you have to fetch it from main memory. Okay, I hope everyone is familiar with this thing, right? So how is the block found if it's in the cache? So so if tag of every cache block that so I'm going to just move on because we have done that. Now when talking about direct mapping, it's easier because when you're talking about direct mapping there is only one place. Now if you talk about set associative, then in a set associative cache then a set is defined. When there is a set defined, this means there is not a single line defined but a set defined. So if it's two-way set associative or four-way set associative, then this means you have got multiple options. So what do you do? For example, you do it in the same way you could reach a particular set. And when you reach a particular set, say for example set number 0. Now set number 0 has got two lines. So this means you are going not to a particular line. So this means you don't have a one tag, but you go to a particular set which has got multiple lines, which means you have multiple options. If you have got multiple options, this means that you can come you need to search both these options to know whether you have that data with you. So previously we were searching only a single line, but now what you need is another comparator which is going to compare the value of the same tag with the other. I'm going to redraw this. You need another comparator and you need to compare the other tag with the tag coming from the address to know whether you have a match. So you are going to have a match in any one of them, not both of them. So you cannot have a match in both of them, right? And it's a possibility that none of them matches as well. So when both of them are not matching, this means there is a miss. If one of them matches, it's a hit, right? Now, how are you going to compare them? Is it going to be parallel or is it going to happen in sequence? That is, you use a single comparator. You first of all compare the first tag, and if you cannot match it, then you go for a second one. If you're going to do like this, then it's going to take a lot of time. So we always go for parallel matching. Parallel matching means we have as many comparators as there are lines in the set, right? And all of them are taking the value of the tag from the address and comparing it with their own values. And if there is a match, then there is the word that you need. And if there is no match, then this means that you have to fetch it from main memory, right? So this is how the whole thing works. So if you're talking about a set associative map, you don't have one line, but you have a set, and then you have to match both these tags. Now, if you have a fully associative map, in a fully associative mapping, what happens is the cache is interpreted in only two fields because there is no set field. So it's only a tag and a word field. Now there is no set field. So that was the first field which we were using to go to that particular position and then select a particular set or a line to then continue on with comparison. But if you're talking about a fully associative cache, there is no concept of set there or a line there because a block can go to any place. So in that case, there is no set or tag. So there is no set or line. There is only a tag. So this means that if you're talking about a fully associative map cache, then its tag portion is a bigger portion. The stack memory is a bigger memory. So for every line there is a tag, because then there are different. Because if you continue with if you go to the example that we were doing there. So in a fully associative cache, we said that every block can come to any line. Any block can come to any line. This means that there are 8 possible options over here. And if there are 32 blocks, in order to identify which block is occupying one line, we need to have a tag which can identify all these 32 together. So if there are 32 blocks, we need at least 5 bits. We need at least 5 bits to determine which one is there. So this means if you need a memory over here for every cache, that memory has to contain 5 bit of information, because that 5 bits is going to identify these 32 blocks. right? So you need a bigger memory in this case. So and then what's going to happen is then it's going to compare with all of them in parallel. So you need as many comparators as there are lines in the cache, and this tag field is going to be compared with all of them in parallel, because this operation can happen in parallel. So you are going to compare the tag with all the lines in the cache. So it's obviously a complicated task. It's also a power consuming task because you are comparing all the tags. If there is a match, that match is going to come from any one line. It can't be from more than one line, or there can't be any match from any line. That's also a possibility that none of the lines matches. But if it's going to match, it's going to match only one line. So if there is a match and you identify a particular line, that word field is going to do the same thing. That's going to select that particular word from that uh, from that particular line, and then it's going to pass on that word to the CPU, right? So this is how it works. So I'm sure now you know how it's going to be done. So this was just a revision for those who have studied that earlier as well, but these things are easily forgotten. So it's better if you have a if you have a revision over here. So in set associative and associative caches, all possible tags are surged in parallel. That's the important thing. All of them are surged in parallel because the reason for using cache is to improve the speed. And if anything is done which is going to slow down, then it's not going to be beneficial. Okay, then there could be some valid bit added to the tags to make that entry valid. If you're talking about getting that reading that for the first time. So if you are doing that for the first time, for example, you have powered on the system, so there will be some random data in the cache, and if you want to search within the cache, maybe you get some matching, but that's not a valid thing. So you include a valid bit along with with every line, so that initially whenever you are powered on, all these valid bits are zero, which means they are not valid. And whenever you are going to bring some useful information from main memory into the cache, then only you're going to make that valid bit one. This is going to ensure that if you are going to power on the system, then it's not going to start matching it. Okay, our third question is, which block should be placed on a cache miss? So which block should be replaced? So if there is an option for replacing a block, which block should be replaced? Now in a direct map, that's very easy because it's there is only one place for a block to come. So if a new block is also mapped to the same space, there is no other option. You have to remove that but previous block, and that's the only option. When you're talking about set and fully associative caches, then there are different options for a block to come into the cache. So if you're talking about fully associative, it can come to any line. If you're talking about set associative, it can come to any line within that set. So then the question comes, which block should be replaced? So if you want to remove some block from the cache, how you're going to select a block? Now there are two common strategies for doing that. The easiest is not an algorithm, but it's a random policy, which is to randomly select a block and throw it out from the cache. So this is implemented. This is quite easy to do because you don't need any complicated data structure to handle which block should be replaced. You just select a block using a pseudo random block generator, which is a small circuit, which is going to give you a bit sequence, which is going to be the block number or line number, and whichever line number is that, you just throw that block out from the cache and bring the new block in its place, right? Then if you want to do it, if you want to do something which is more algorithmic and more reasonable, then you go for some known algorithms like least recently used. Now in a least recently used, you look for a block which is the one which is there in the cache the earliest and hasn't been used, right? So is the least recent. So if you compare the least recent with its antonym, which should be the most recent, then you can easily understand what least recent means. So most recent means that most recently used would be the one which is the most recently used block, and least recently one would be the one which hasn't been used for a long time and it's still there in the block. So you're going to remove that block. I'm not going to go into detail how they are implemented, but there are different hardware like counters or different other mechanism bits to manage that. Least recently used is also in an actual form never used in implementing any block replacement. So you have got an option like pseudo least recently used, which is a better option because it looks for portions of the caches which have not been used recently, and then it tries to find out from that within that portion, it tries to find out which blocks should be removed, right? So that's another way to do that. Again, pseudo least recently used is the common term, but I'm not going to go into detail for that. You can look for that yourself. How is pseudo least recently used policy implemented? Then there can be other options, but they are not viable. Like for example, least frequently used. You look for the frequency of the block and then suggest which block should be removed. Okay, let's come to our fourth question. What happens on a write? Now, when there is a write operation, you change the elements, you change the data. So how are you going to change that in the other levels? That's the main question. So before that, we need to answer the question: how often do we write? Now, many times you're going to see that there are more reads in an instruction than writes, because writes are only going to happen when you are going to have a store instruction. Otherwise, all the fetches are reads, all the load operations are reads. So you are only going to write very infrequently, right? Because read dominates more. So the main thing is writes are less frequent operation, but still they are going to be writes. So there are two different strategies. One of them is write through, the other one is write back. When you're saying write through, this means that the information has to be updated in both the cache and the main memory. Okay. Now it never says that it has to happen at the same time. But people do get confused that when you say write through and the information has to be written down both in cache and main memory, and that has to be done simultaneously. That's not the main thing, that it has to be done simultaneously or it has to be done at the same time. The main thing is that both have to be written. So if any word change in the cache has to be propagated to the lower levels like main memory and other levels, right? In a write back scheme, what happens is you only write to the cache. You don't write to the main memory. So this means that the data in the cache and the main memory are inconsistent with each other. And then you cannot say that it's a copy of the same thing which is in the main memory, because the more updated one is in the cache, the modified one is in the cache. So how are you going to modify it finally? So in that write back scheme, what happens is when you select that block for replacement, when you select finally that this block has to be removed from the cache, then only you remove it and place it in the main memory, right? So in a write through scheme, you're always going to write to cache and main memory. It doesn't has to be simultaneous operation, but it has to be there, and you are finally going to write it down. Whenever you're going to write to cache, you are also going to write to main memory. It's going to take some time. It doesn't mean that you cannot do anything within that time. When you are writing to the main memory, the processor can continue. There are other options for that, but you have to update main memory. When you're talking about write back, you don't have to update memory. You only update the cache, and you only update memory whenever that block is removed from the cache, not before that. Okay, so these are the two different schemes. What happens on a write? Again, the same question. And continuing with the previous question, Now there can be different options when you are going to write to a block of memory, block of data. When we're talking about reads, for the read operation, you have to fetch the data from memory. Okay, but for the write operation, uh, it's not necessary that you bring that if it's not already there in the memory. If it's not already there in the cache. I'm going to repeat. If when you're talking about a read operation and you want to read something, it's necessary that you have to have that thing in the cache. But when you run to write something, it's not necessary that you have that thing in the cache if it's not there already, right? So if it's not there already and you want to write that thing, you can directly write it in the main memory as well. Okay, so there are two different schemes for that. Write allocate. So if there is a write miss that you want to write to something and it's not there in the cache, write allocate says bring it in the cache and then write in the cache first. Okay, so again, so in a write allocate policy, what happens, you want to write some data and that data is not in the cache, so there is a write miss. So in the write miss, what options do you have? If the data is not there in the cache, what options do you have? Should you bring that data in the cache and then write it, or do you need to write it directly in the main memory? Because if it's not there in the cache, do you feel that it's necessary to bring it in the main memory in the cache and then write it? Obviously, if you think that there would be some temporal locality and that item would be referred again, then you need to bring it. But if you feel that right, if it's not there in the cache and you can just handle it without bringing it into the cache, then you can directly write it in the main memory. So there are two different schemes. Write allocate says bring that block in the cache and then write it. No write allocate says only write it in the main memory. If it's not in the cache, don't bring it in the cache. Just update the main memory. Okay. And these write allocate and no write allocate can be combined with write through and write back. So you can have a write back with write allocate or write back with no write allocate, or you can have a write through with write allocate and write through with no write allocate. Okay. So these are terms that you have studied earlier. So I'm going to just go through the next topic. So we are continuing with our lecture today without any break. Because I'm going to continue till 1:30. What time is it? It's close to 1. So what do you need a break? So we can have a 10 minutes break and then we can continue, or do you want to continue and finish earlier?
Sir, you can continue now.
Okay, so let's continue. Okay, so let's continue.
Continue करें, लाइट का कुछ पता नहीं है.
Okay, let's continue. Okay, so what the last point here was both write through and write allocate use write buffers to make write. Okay, so then there is another thing, write buffers. Now, as I said that write through is not necessary that you write it simultaneously. Whenever you're going to write to cache, you simultaneously write to the main memory. No, that's not true. Then there is you can say an optimization in the system is that we have a write buffer. Write buffer is something, it's called a buffer which takes the data that you need to write and also takes the address that you need to write. And then what it does is it loads that write value that you have written to the cache into the write buffer. Instead of writing it to the main memory, it writes to the write buffer only and then assumes that the memory has been written. So the processor is now satisfied because it is going to write to the write buffer only, which is a fast memory, a small memory. So whenever it's going to write to cache, it also writes to the write buffer. And when it writes to the write buffer, it assumes that the task of writing to the main memory has also finished. Now, what the write buffer does is it looks at the main memory and sees when the main memory is free for any write operation. And when the main memory is free, then it performs that write operation. And that particular entry from the write buffer is then removed. So if you're talking about a modification here, we see here that um, uh, the CPU is going to write to the cache, and then there is a memory. So it has to write to the main memory, but it never writes to the main memory. It writes to another memory which is called as a write buffer. So there is a write buffer here which has got different entries. Each entry has got some address and data space. So CPU is going to write to the cache and the write buffer, and write buffer is as fast as the cache as well. So it has got different entries, and obviously there are limited entries. So you cannot have unlimited entries over here. So when the CPU writes to write buffer, then it thinks that it has written to the main memory. Write buffer is going to write to the main memory at its own time when it feels that the main memory is now free. Okay, from the CPU point of view, it assumes that writing to write buffer is same as writing to the main memory, and main memory would be updated somehow eventually whenever the write buffer is going to get time. Now it can also happen that write buffers had pending writes and more writes were provided by CPU and all the fields have been full. When all the entries of the write buffers are full, then no more writes can happen, and then CPU has to wait. Now in that case, the write buffer is going to first of all finish its writes to the main memory, and then the CPU can continue. So you see here the CPU is not stopping all the time, it's only stopping when the write buffer entries are full. Okay, so that's the modification that is defined over here. A common optimization to reduce write stalls is to use a write buffer. Write stall was the term used for whenever the processor has to wait. So the processor does not have to wait for all the writes. It can write to the write buffer and then continue, right? Only when the write buffer entries are full, then the processor is going to wait for the writes to happen. So both write through and write back have write buffers. So it's easy to understand why write through will have a write buffer. Why do you think write back has write buffer? I mean, write through is going to write to both writes, both cache and main memory. That's why write buffers are there for write through caches. But why is there a write buffer for write back caches? Because in write back caches, you are not going to write to the cache and main memory. You're only going to write to the cache. So why do you need a write buffer if you are only writing to the cache? Why do we need a write buffer for write back cache? Because in write back cache, we are not going to write to the main memory. Whenever we need a block to be replaced, then only that block is going to be written to the main memory. So why do we need a write back cache? Why do we need a write buffer in this case? Anyone? Again, the same concept, because if you're going to write something back to the main memory, there's a whole block that has to be written, right? From cache to main memory. So if you're going to wait for this whole thing to happen, then obviously the performance has to suffer. So what happens is then we don't write directly from cache to main memory. So what we do is the cache is also going to write to the cache is also going to write to the write buffer, and then it's going to write to the main memory at its own time. Okay. So in both write back and write through caches, we use write buffers to make write asynchronous. To make write asynchronous means that that's not happening at the same time when it's expecting the writes to happen. They can happen whenever the memory is empty or free to do its task. Now this is an organization of the data cache in Opteron microprocessor. Is just shown for an example how a real processor is working with its cache. So it has got an address of 25 plus 9 plus 6, that's going to be 40 bits. So 40 bits address is generated by CPU, and 6 bits are reserved for the word field, which means that the block size is 2 raised to power 6 or 64 bits. So there are 64 words in a block. The index field is 9 bits, which means there are 512 512 lines, right, or sets, because the index is defined here. It's not defined as line or set. And then we have a 25-bit tag, which means that there are going to be 2 raised to power 25 different blocks that can occupy the same uh, line or set, right? So what happens is, first of all, you index into the tag using this index field. Using this index field, you index into the tag, and then you compare their tags, right? So it's shown here as two different memory, which means that it's a two-way set associative. So it's the sets are defined in this way, that this thing and this thing is part of a single set. So both of these lines are part of single set. So we have a two-way set associative cache in this case. So this means that we are going to select in both these the second the line which is represented by this index field, and within that we are going to compare their tags. And when the tags are compared, if there is a hit, then that particular word is then going to be passed on. If there is a miss in both these cases, then we are going to go to the lower level, right? Otherwise, the data is going to be passed on from the data portion into the data cache. Okay. Right. So if that was a four-way associative cache, you would have arranged that into 4 different cache blocks, and then you can do the same thing in this way. Okay. So then we have a problem, but I'll leave that for you to do. If there is any difficulty, you can ask me. It's a simple problem. Let's come to our main memory optimization. So we are going to discuss about 6 basic cache optimizations, and then we have got 10 advanced optimization. Those 10 advanced optimization would be studied in the next lecture. Today we are going to talk about the 6 basic cache optimizations. So when you're talking about memory access time, we define the access time as the hit time plus the miss rate into miss penalty. Okay, so I'm going to come to that. What do we mean by this? Okay, so we have again CPU, cache, and main memory, say. So main memory has time T, let's talk about T2, and cache has time T1. Okay. Okay, so T2 time is actually a combination of the block transfer time plus T1. So when you have a cache, you're not going to access main memory directly. So if you want to get something from main memory, it's actually the time it takes to load the block into the cache and then access the cache, right? So CPU is always accessing the cache, right? So CPU is always accessing cache. If it cannot find that element, it has to be fetched from the memory, but then it has to be transferred into the cache, and then the transfer has to be reinitiated, and then you are going to take the same time, TB plus T1, that's T2. Okay, so we need to find out what should be the average access time. Now you know that average is going to lie between T1 and T2 because average is obviously going to be greater than T1 because that's the faster memory, but not all the references are going to be satisfied over here. So some of the references are going to go to T2. So if all of the references were going to T2, then TA should be equal to T2, but you know that since many of the references would be satisfied in the cache, so this means that TA is going to lie somewhere here in between T1 and T2. But we need to find out what should this be, what should this value be. So how to find this out? So we need to find out how many references are satisfied by the cache, and for how many references do we have to fetch that from memory. Because for if we have say 100 references and 90 of them are satisfied over here and 10 of them are satisfied over here, this means that for 90 references we are going to take this time, and for 10 references we are going to take this time. And then if you want to find the average, that average would be then 0.9 into T1 plus 0.1 into T2. Is this thing clear? That's quite easy, right? So, but how do we get this number 90 or 10? Right? So we define here some hit rates depending on when we have executed a program. You can determine how many references were satisfied by cache. Now that can be only done if you have run that program, not earlier than that. So average memory access time is then the hit time plus the miss rate into miss penalty. Okay. If I ask you to do it yourself, what are you going to do then? What are you going to write then? So if I ask you to write average access time, how are you going to determine depending on this? So let's say we say 90% of that. So 90% is then our hit rate, right? So we get something which we can say. So 90% of the time we are accessing. So I'm going to call that as hit rate. So I'm going to call that as H. So 90% of the time we should get T1 and the remaining we should get it from T2. So that should be the average access time, right? So this thing that I have mentioned over here, HT1. Now, as you know that T2 is actually TB plus T1, right? So why not we write the same thing in this way? So we can say it's going to be H T1 plus 1 minus H TB plus T1 right? So you see here there is HT1 and there is 1 minus HT1 as well, which would mean that it's going to be T1 plus 1 minus HTB. Right? Is this thing clear? Because there is H and 1 minus H for T1, so this is going to be just T1. And then there is 1 minus TB. Now this formula over here, what is T1? T1 was the time for cache. So that's the hit time. What is 1 minus H? That is the opposite of the hit rate. So we are going to call that as the miss rate. What is TB? TB was the block transfer time. So we are going to call that as the miss penalty, right? Or the time that is taken for the block to move from here to here. So this is hit rate plus the miss rate. Sorry, hit time. It's the time, not the rate. Hit time plus the miss rate into the miss penalty, right? So that's the same thing that we have written over here. Hit time plus the miss rate into miss penalty, right? Now, if you need to improve average memory access time, improving the average access time means you need to have this time as low as possible. So if you need to have this thing low, you need to have any one of this thing low. So either you can go for reducing the hit time or reducing the miss rate or reducing the miss penalty. So there can be different options. So we are going to look at the different options today. Reducing the miss rate means we can have larger block size or larger cache size or higher associativity. Reducing the miss penalty means we can go for multi-level caches or giving read priority over writes. And reducing time to hit in the cache means that we can have better way to access the first level of the cache, right? So we can go for schemes like avoiding translations when indexing the cache. Okay, so let's see how much we can do today because we have got 20 more minutes now or maybe less. Let's see. Okay, so the first optimization, larger block size to reduce miss rates. So these are the easier ones, so I'm going to just go through them quickly. What do you get in your mind when you read this word, larger block size to reduce miss rate? This says if you have a larger block size, is going to reduce miss rate. Is this thing true? So the simplest way to reduce miss rate is the amount of um, the amount or the fraction of accesses that you cannot find in the cache. So if you want to reduce this miss rate, you in other words want to increase the hit rate. So how can you increase the hit rate? You can increase the hit rate by increasing the block size. Is this thing fine? Is this thing okay? Yes, anyone? So what we are saying is if what we are saying is if you need to increase the hit rate or decrease the miss rate, you can increase the block size. So previously we had 4 words in a blocks. To increase the block size, let's have 32 words in a block. So how is this going to reduce the miss rate if we have larger
Sir,
blocks?
sir, there are four possibilities to hit to get the hit option, but now we have 32 option to ignore the miss rate. Means 32 option to hit it.
Actually, if you are going to have more words in a block, there is something related to the program's behavior that we have just discussed. How is that going to affect that? I'm trying to ask related to that particular behavior that we have determined. If we are going to increase the block size, which particular thing is being affected, and that which, or in other words, can you say which particular miss is going to be reduced in this case? Anyone? If we increase the number of words in a block, which particular miss? We have got 3 types of misses: compulsory misses, conflict misses, and capacity misses. If you increase the block size, which particular miss is going to be reduced?
Sir, I think so capacity miss.
Capacity miss. How can capacity miss be reduced? In fact, capacity miss seems to be increasing, because if you're talking about increasing the size of the block without changing the cache size, what effect is this going to have? Yes, anyone? If you're increasing the block size, this means that you have got more words in a block, which means that previously if any word was referred as a separate block, now it's part of this block. Okay, which means that if you're going to fetch any word from this block, automatically you are going to bring in this one as well. Okay, it's because your word size is big. So if you are going to fetch this, you're going to bring the whole thing, which means this one and the other one as well. So the next time if you want to refer to this is not going to be a miss, but it's going to be a hit, because that block is already there. So what type of miss was that has been reduced? That was a What type of miss was that? That was a compulsory miss. That was a compulsory miss, which was the first miss to any block. Because the block size has increased, you have reduced the compulsory misses. All those misses which were for the first reference for the block. But since the block size is big, you have got more references that you can satisfy. So the compulsory misses are going to reduce, which means that the miss rate is going to reduce. But the other thing is that you are not changing the cache sizes. And if you're not changing the cache size, this would mean that a bigger block is going to come into the cache. This means that there would be more conflict misses and more capacity misses, because the capacity is quickly going to be occupied, and more conflict misses because the cache size has an increase, and then you are going to have less lines in the cache if you're going to increase the block size. So this option is good, but it's not going to reduce the miss rate too much. It's going to reduce it initially, but if you're going to keep on increasing the block size, then you are going to increase the capacity and conflict misses. So if you look at the graph over here, you're going to see as we increase the size, so as the size increases, the miss rate reduces initially, but then if you increase the size further, a time would come when your compulsory misses, the advantage that you were getting for reducing the compulsory misses is less than the disadvantage that you're getting for increase in the conflict and capacity misses, which means that the overall miss rate starts increasing beyond a particular size. So there is some size which is going to give you the best miss rate, but then it's going to decrease. It's going to start increasing, right? So you're going to see that there are going to be some sizes for a particular for a particular cache, for a particular capacity of cache. There is a particular size which is going to give you the best miss rate, and afterward it's going to start increasing because the conflict and the capacity misses are going to increase. The second optimization is to have larger caches to reduce miss rate. Now this is a very easy one because if you have got bigger caches, you can handle more elements, and this is obviously going to reduce the miss rate. So I'm not going to explain more on this. The third optimization is is there any question over here? Because I feel this is very easy. Because if you are going to increase the cache size, obviously more elements can come in, and this means more hits are going to occur, and so this is automatically going to reduce the miss rate, right? So we are not talking about anything done to the block size. We are just talking about increasing the cache size, which means there are more options for. We are not talking about any power issues here, but we are talking about cache sizes. So cache increasing the cache size is going to obviously reduce the miss rate. Is this thing clear? Okay. So then a third optimization is higher associativity to reduce miss rate. So instead of a direct map cache, if we have got a two-way set associative cache or a four-way set associative cache, then this means there are more options for a word to come in. And this is obviously going to reduce the conflict misses. So because there are less conflicts, then this means that the miss rate is also going to reduce. So a rule of thumb is that an n-way set associative cache is gives you a same miss rate as a n by 2 two-way set associative cache, right? A fourth optimization is to have multi-level caches to reduce miss rate. So if you have got multi-level caches, like instead of having just a single level cache, you have many levels of cache. This is going to reduce the miss penalty. Now here we are not talking about miss rate, we are talking about miss penalty. The time taken to get that data from the previous level. So obviously when you have got multi-level caches, the whole equation changes because you're not talking about only a single level, you're talking about multiple levels, and each level has its own access time. So if I come back to that formula over here, when we're talking about access times over here, so we were discussing these access time using just two levels. If I introduce another level in between, so if I have can I cannot cut this thing. Okay. I was thinking about cutting this, but I cannot do that over here. Can I do this? No, that's text. Okay, so there is no option over here. So I have to redraw. So I'll just redraw it. So there is a CPU, there is a cache over here, and there was a main memory, right? So main memory had a time of T2. This was a T1 time over here, right? So what we are saying is that in order to reduce the miss penalty, the penalty from going from here to here, which was taking a lot of time, that can be done if we have got uh, another level in between. So we are going to call this C1 and this is C2. And this time, let's take this time to be So I'm going to rename them T2, and let's take this thing to be T3. So we have T1, T2, and T3. Now we have introduced another level. Now how are things going to change? So this one was H1. Now this is going to become H2, and this is going to become H3. H is the hit ratio, or the number of references that can be satisfied over here. Now obviously all references can be satisfied in main memory, so H3 is always going to be 1, because this is your last level and every data is going to be there. So the probability of finding anything in this level is going to be the maximum. So we are going to call that as 1, because everything is going to hit over here. If the CPU directly had access M, it would have found everything there. So the hit rate is 1. But hit rate of H1 is going to be less than hit rate of H2, and it's going to be less than the hit rate of H3. So from the same formula, what if you want to find the average access time, you can go from the same formula, which would be 1 minus H1 T1. What is the probability that you can get this item? You can find this item in the first level, and what is the time for that level? Plus, what is the probability that you couldn't find that element in the first level, but you found that in the second level with the time of that second level, right? Plus, what is the probability that you cannot find that in the first level and in the second level, and you found that in the third level with the time of the third level, right? So you see here that this was already there, but the second part has been reduced by this. And because this thing is going to be very small, meaning that the time that you're going to refer T3 would be the number of times that you're going to refer to this memory level is going to be also few. So this means more of the time you are going to refer to T2 than T3, right? So for example, in our earlier question, if we said that 90% of the references were going to C1 and 10% were going to memory, of those 10%, 8 are going to be cached C2 and 2 are going to memory. So you're going to see here that this is not going to be affected. The 90 was already there, it's still going to be there. What you have done is, instead of having 10 references taking time of T3, you have broken that down. 2 are taking T3 and 8 are taking T2. And obviously you know that T2 is less than T3. This means that average access time is going to reduce, right? So average access time is going to reduce because 8 times you are referring to T2, which is less than T3, right? So I'm going to stop over here with the fourth optimization. So this is what we have done. So average access time is going to be then the hit time plus miss rate of level 1 into hit time of L2 plus miss rate of L2 into miss penalty of L2, right? So we are going to continue with the fifth optimization onwards, and then we are going to have some advanced optimization. And next class would be next Thursday, inshallah. This was a compensatory class that we missed for. We have missed 2 classes. One was the initial one that we didn't take for the first week, and then we missed one due to rains. And so this one, let's consider that to be the rain one. And then we are going to have one midterm next Sunday, and that is going to compensate for our earlier. And then we are going to come to the normal schedule, right? So midterm, I'm trying to have a midterm which is easier for you people. So and then there were issues this time because there were different students who had this problem of not studying properly due to rains, and so 1 week delay was there, right? So I thought that I should go with a 1 week delay instead of forcing you to do it
Thank you, sir.
this week, so that you get some time to go through those lectures, right? Okay, so I'm going to stop over here. So just write your roll numbers in the chat so that I would know who was here. Maybe all of you know 6, 7. There was one more over here, but yeah. Okay, just write your roll numbers in the chat and then you can leave. So I'm going to stop over here.
Excuse me, sir.
Yes.
Sir,